The universe has a beginning in real time, at the Big Bang. And it may well have an end, if it collapses to a big crunch. But in imaginary time, it has no beginning or end. I am very aware of the preciousness of time.
Time is one of the biggest mysteries of the universe because its existence leads to some paradoxes that remain unsolved today. Scientists have been trying to understand the nature of time and how it began. Time travel is yet another paradox that continues to haunt scientists. Recently, famous physicist Brian Cox announced a new time paradox that has shocked and terrified scientists around the world. So what is the nature of time? How does it shape our existence? And what new time paradox has emerged that left scientists scared?
You know, even very simple things, like you go back to the Greeks, so Aristotle and very clever people, but they thought the Earth was at the centre of the universe. Why? Because it feels like it feels like we're not moving. And that's quite a deep point, actually, in physics. It's like, why is it that we're flying around relative to the sun very fast at whatever speed it is, 18 miles a second or something like that, and the whole solar system is going around the Milky Way galaxy and so on? But why is it that we don't feel it? The Greeks quite naturally said, well, because we're at the centre of the universe. They also said everything falls towards the Earth, so therefore the Earth must be at the centre. It's natural. And actually it's quite a deep thought to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. Well, he said, well, there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't tell whether you're moving or not demolishes the notion of absolute space. So if we think about space, if I said space, you'd think the way that Newton did, of a big box within which things happen. That's a natural picture of space and the universe, isn't it? It's a thing in which all the planets and galaxies are placed. But Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. So I drop it and I catch it again. So let's say I drop it and it takes a second to bounce up. So in that second, the Earth has moved about 18 miles or so in space around the sun. So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can't answer it. It does from our perspective, but from the perspective of someone watching the Earth go all the way around the sun, when I caught it again, it had moved 18 miles. From some other perspective, it would have done something else. So the point is, you can't say this is a point in space. It came back to the same place, because that just depends on your perspective. Depends on whether you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space, which kind of follows if you think about it. But that's it's cool, but difficult thought process.
When we die, our bodies break down and become part of the Earth, helping new life to grow. So in a way, we keep going through these processes. But could there come a time when there's no more after at all? Modern physics suggests that this could happen. Time might stop completely, meaning no new beginnings or cycles. If time ends, it would be the end of everything.
Time is defined to make motion look simple, because you cannot describe motion without some reference to time. I also think of time as this prison. Time makes us all a prisoner of the present, forever transitioning from our own past into an unknown future. And that's particularly disturbing to me, because we can move back and forth in any other coordinate. Up and down, left and right, forward and back, but we're stuck in time. We can't move forward or backwards in time arbitrarily. So that coordinate has a kind of a fundamental difference from the other three. Now, my professional ancestors, the earliest astronomers, basically invented timekeeping, all right? So all measures of time historically were derived from cosmic rhythms. So today we would say the rotation of the Earth, but in the day it was the movement of the sun. Yeah. So that gave you a day, and then the sun's position on the sky throughout the days differed, and temperatures changed, so that gave us the seasons. And then, of course, back then it was the sun doing all this, but we would learn that we rotate and we revolve around the sun. So that took really long to figure out, disturbingly long. I mean, only like 400 years ago So what it tells you is that you can keep track of time even though you have no freaking idea what's going on. Because all that matters to you is that things repeat.
Yeah.
If you have something that repeats predictably, then you have created a timekeeping mechanism.
Before Einstein's theory of relativity, people thought time was constant, like a clock. Einstein showed that time is more like a changing musical performance. It can speed up, slow down, or act unpredictably. Gravity affects how we experience time. Objects are drawn to places where time moves slower. Time isn't a steady flow. It changes based on its surroundings. In some chaotic situations, time might even disappear completely. When time reaches its extreme limits, we call these points singularities. They can mark the start or end of time. The Big Bang, which happened about 13.7 billion years ago, is one famous example. If the universe stops expanding and starts collapsing, it could lead to the Big Crunch, where time might end. But inside black holes, time stops while it continues elsewhere in the universe. Black holes are incredibly destructive. If someone were to fall into a black hole, they would be pulled apart and eventually reach a singularity where time stops. This is like the end of a story. Not just dying, but a total collapse. Physicists are trying to understand singularities better. They're working on a theory that combines Einstein's ideas with quantum mechanics, called quantum gravity. This might help explain or avoid singularities. The idea of time ending is hard to grasp, and the idea that it might never end is just as confusing. Before Einstein, philosophers debated whether time could end. Immanuel Kant saw this as an antinomy, a situation where both sides of an argument seem true but conflict with each other. Aristotle also thought about time, suggesting it can't have a beginning or end. Every moment marks the end of one period and the start of another. So how could time ever stop? What would prevent the last event from causing another? How can we define the end of time when the idea of an end relies on time existing? Oxford philosopher Richard Swinburne argues that it's logically impossible for time to end. If time is endless, then the universe must be infinite, raising complex questions about infinity. The Big Bang Theory and black holes suggested that the universe might face scenarios like the Big Crunch or the Big Rip. However, understanding singularities remains unclear. Lawrence Schuyler, a philosopher in physics, notes that the physics of singularities is still uncertain. Some theories suggest singularities might not truly exist. For instance, the Big Bang singularity is thought to have compressed all the material into a point with zero size. Inside black holes, everything is squeezed into a tiny point. These calculations often lead to infinity, which is problematic. Physicists are working on a new theory called quantum gravity to understand these extreme situations better. They believe that if matter behaves like a wave rather than a point, it could prevent the problem of infinity. Now, if this is true, time might not end after all. Physicists debate both sides of the argument. Some believe that time does indeed end, but this poses a challenge because the known laws of physics operate within time and describe how things move and change. The end of time would require not just a new law of physics, but an entirely different type of law, one that doesn't rely on temporal concepts like motion and change, but instead emphasizes timeless principles like geometric symmetry. For example, Brian McInnes of the National University of Singapore proposed an idea based on string theory, a leading contender for a quantum theory of gravity. He suggested that the early universe might have had the shape of a torus, a donut-like structure. Mathematical theorems about tori require uniformity and smoothness. However, at a big crunch or black hole singularity, the universe could take on any shape, and the same mathematical principles might not apply, leading to an irregular universe. This geometric law of physics differs from traditional dynamic laws because it lacks symmetry in time. The end wouldn't simply be the beginning in reverse. Some researchers in quantum gravity believe time stretches endlessly without a beginning or an end. They see the Big Bang as a significant transition in the ongoing life of the universe. According to this view, the universe might have started contracting in a big crunch before rebounding when the density became too high, a phenomenon known as the Big Bounce. Traces of this prehistoric era might still exist today. Similarly, the singular bundle of the core of the black hole might behave like a miniature star, boiling and bubbling. If you were to fall into a black hole, it would be a painful end, but your timeline might not cease entirely. your particles would enter the bundle, leaving a mark that future observers might detect in the faint light emitted by the black hole. Proponents of the view that time continues indefinitely avoid speculating about new types of physical laws, but they face challenges. For instance, the universe tends to become more disordered over time. If it's existed forever, why isn't it completely chaotic? Also, how could the light carrying your imprint escape a black hole's intense gravitational pull? The struggle with paradoxes and understanding time isn't unique to physicists. Philosophers have dealt with similar issues for centuries. John Archibald Wheeler, a prominent figure in quantum gravity, famously remarked, "Einstein's equation says that this is the end, and physics says there is no end." Some people conclude that science may never definitively resolve whether time has an endpoint, seeing the boundaries of time as the limits of reason and empirical observation. However, others remain optimistic, believing that with innovative thinking, physics can eventually provide a clear answer. Physicist Gary Horowitz of UC Santa Barbara asserts that it's not beyond the realm of physics. Quantum gravity should be capable of providing a definite solution. As physicists and philosophers grapple with the concept of the end of time, many draw parallels within the end of life itself. Just as life emerges from inanimate molecules organizing themselves, time might arise from some timeless substance that self-organizes. A world with time is one with structure. Time helps us understand when events happen, how long they last, and their sequence. Perhaps this structure isn't imposed from outside, but rather emerges from within. Just as what's built can be dismantled, when the structure breaks down, time ceased to exist. According to this perspective, the end of time is no more perplexing than the breakdown of any other complex system. Gradually, time loses its defining characteristics and transitions from existence to non-existence, much like passing through twilight. The first aspect of time that might disappear is its one-way directionality, the arrow pointing from the past to the future. Physicists have understood since the mid-19th century that this arrow is not an inherent property of time itself, but rather a characteristic of matter. Time inherently flows in both directions. The arrow we perceive is simply the natural progression of matter from order to disorder. This initial orderliness may stem from geometric principles proposed by Macinnes. If this trend continues, the universe will eventually reach a state of equilibrium known as heat death, where it cannot become any more disordered. While individual particles will continue to rearrange themselves, the universe as a whole will stop changing, and any remaining clocks will oscillate in both directions. The distinction between the future and the past will blur. Some physicists have speculated that the arrow of time might reverse, causing the universe to tidy itself up. However, for beings whose existence relies on a forward arrow of time, such a reversal will signal the end of time as surely as heat death would. Recent research suggests that along with the arrow of time, another fundamental aspect that time might lose is the concept of duration. In our current understanding, time is measured in units like seconds, days, and years. Now, without these units, we could still perceive events occurring in chronological order, but would be unable to determine their duration. The idea is proposed by University of Oxford physicist Roger Penrose in his book Cycles of Time, an extraordinary new view of the universe. Throughout his career, Penrose has been deeply interested in the nature of time. In collaboration with physicist Stephen Hawking in the 1960s, he demonstrated that singularities, points of infinite density, should be a common feature of the universe, not just in special circumstances. Additionally, Penrose has argued that matter falling into a black hole ceases to exist in any meaningful sense, and that time might not play a role in a truly fundamental theory of physics. In his latest work, Penrose starts by examining the early universe. At that time, it resembled a disordered collection of particles, much like a box of Legos scattered on the floor awaiting assembly. This chaotic mix included quarks, electrons, and other elementary particles. Now, from this chaos, structures like atoms, molecules, stars, and galaxies gradually formed, one step at a time. The first significant step occurred about 10 microseconds after the Big Bang, or Big Bounce, as some theories suggest. This step involved the creation of protons and neutrons, each consisting of 3 quarks and measuring about a femtometer across. Before this event, there were no coherent structures. Nothing was composed of bound-together pieces. Consequently, there was no framework for timekeeping. Clocks rely on the stable reference, such as the length of a pendulum or the size of atomic orbitals. However, at this early stage, no such reference existed. While clumps of particles may have temporarily formed, they lacked a fixed size and thus couldn't serve as a reliable time reference. Even individual quarks and electrons, the building blocks of matter, have no discernible size. When closely examined, they appear as mere points to particle physicists. The only attribute resembling size is their Compton wavelength, which determines the scale of quantum effects and is inversely related to mass. However, even this rudimentary scale was absent before a time of about 10 picoseconds after the Big Bang, when the process responsible for imparting mass had yet to occur. There was no way to keep track of time, Penrose explains, without anything capable of marking regular time intervals. Whether an attosecond or femtosecond passes makes no difference to particles in the primordial soup. Penrose suggests that this scenario not only characterizes the distant past, but also the distant future. Even after all the stars have faded away, the universe will be left with a bleak mixture of black holes and free particles. Eventually, even the black holes will decay, leaving only the particles behind. Most of these particles will be massless, like photons, rendering the construction of clocks impossible once again. In alternative scenarios, where the universe ends in events like a big crunch, clocks wouldn't fare any better. You might think that duration would still exist conceptually, even if it couldn't be measured. However, researchers question whether a quantity that can't be measured, even in theory, truly exists. To them, the inability to build a clock suggests that time itself has lost one of its defining features. If time is what's measured on a clock, and there are no clocks, then there's no time, says philosopher of physics Henrik Zinner-Nogel at the University of Granada in Spain, who has also investigated the disappearance of time in the universe. Despite its elegance, Penrose's scenario has its weaknesses. Not all particles in the distant future will be massless. Some electrons will likely survive, and it should be possible to construct a clock using them. Penrose suggests that electrons might somehow lose their mass, but he admits that this idea is speculative and uncertain. That's one of the more problematic aspects of this theory, he acknowledges. Additionally, if the early universe lacked a sense of scale, how did it manage to expand, thin out, and cool down? However, if Penrose's theory holds true, it has a significant implication. Despite appearing vastly different, with one being densely packed and the other ever emptying, both the early universe and the remote future lack clocks and other measures of scale. The Big Bang resembles the distant future very closely, Penrose notes. He boldly suggests that they might actually represent different stages of a grand cosmic cycle. According to this idea, when time reaches its end, it will loop back around to initiate a new Big Bang. Thus, Penrose, who has spent his career arguing that singularities mark the end of time, may have discovered a way to perpetuate it. The supposed slayer of time has become its savior. Even if duration loses its meaning and femtoseconds and nanoseconds blend together, time is not entirely extinguished. It still governs the sequence of cause and effect. Unlike space, which allows for various arrangements of objects within it without imposing a specific order, events that occur sequentially in time, like typing on a keyboard and seeing letters appear on a screen, are inherently connected. However, spatial relationships between objects, such as a keyboard and a post-it note, may be unrelated. Under certain circumstances, time could lose even its basic ordering function and become akin to another dimension of space. This idea traces back to the 1980s, when Hawking and Hartle proposed that the Big Bang marked the differentiation of time and space. Inspired by string theory, which suggests that our universe may be a membrane floating in higher dimensional space, these researchers theorized that under specific conditions, time could merge with space. Imagine our universe as a leaf floating in the wind, with us trapped on it like caterpillars. While normally we can move around freely in our four-dimensional prison, if the leaf is buffeted about vigorously enough, we become immobilized. To make any progress along the membrane, we would need to travel faster than the speed of light, which is impossible. Consequently, all processes cease, as they all require some form of movement, which becomes unattainable. Viewed from an external perspective, our life's timelines, formed by successive moments, don't actually come to an end, but instead curve, becoming lines through space. In this scenario, the membrane remains four-dimensional, but all four dimensions become spatial dimensions. Objects are compelled by the membrane to accelerate closer and closer to the speed of light, until their trajectories become superluminal, effectively eliminating time. People experiencing this transformation might not even notice it. Since all clocks would slow down and eventually stop, we wouldn't realize that time was changing into space. Instead, we would see galaxies and other objects appearing to speed up, which astronomers often attribute to dark energy. But could this acceleration actually be a sign that time is turning into space? At this stage, it might seem like time has completely vanished, yet a version of time still lingers. Even if we can't define duration or causal relationships, we can still place events at specific moments and arrange them in order. Recent work by string theorists explores how time might lose this last characteristic. They look into what happens to time at black hole singularities using the holographic principle, a key concept in string theory. A hologram is a unique type of image that creates the illusion of depth while being flat. It makes a solid object seem suspended in 3D space. The holographic principle suggests that our entire universe might work like a holographic projection. In this analogy, a complex system of interacting quantum particles could create a perception of depth, adding an extra layer of dimension not present in the original system. However, not every image can be a hologram. It requires specific programming. If a hologram is damaged, the illusion is ruined. Similarly, not every particle system can generate a universe like ours. It needs precise patterning. When the system initially lacks these regularities and then develops them, a spatial dimension emerges. Conversely, if the system loses its orderliness, the dimension disappears. Consider a star collapsing into a black hole. While the star appears three-dimensional to us, it corresponds to a pattern in a 2D particle system. As the star's gravity increases, the flat system vibrates more intensely. When a singularity forms, order breaks down entirely. This is similar to how an ice cube melts. The orderly arrangement of water molecules becomes the chaotic disarray of liquid. So the third dimension essentially dissolves away. As a spatial dimension melts away, time follows. If you were to fall into a black hole, the time on your watch would vary depending on your distance from the center of the hole, which is determined within the collapsing spatial dimension. As this dimension disintegrates, your watch would start spinning uncontrollably, making it impossible to tell when events happen or where objects are located. The usual concept of space-time stops existing. Practically, this means that space and time no longer provide a framework for understanding the world. Attempts to measure the positions of objects show that they seem to occupy multiple locations at once. Spatial distances lose their meaning, and objects can appear to teleport from one place to another without crossing the space in between. This effect even allows the imprint of an astronaut who crosses the black hole's event horizon, the point of no return, to escape back out. If space and time vanish near a singularity, the event horizon loses its clear definition. String theory doesn't just smooth out the hypothetical singularity, replacing it with a more acceptable concept while leaving the rest of the universe unchanged. Instead, it reveals a broader breakdown of the ideas of space and time, with effects that go far beyond the singularity itself. However, the theory still relies on a fundamental notion of time within the particle system. Scientists are currently working to develop a concept of dynamics that doesn't assume the existence of time at all. Until then, time stubbornly persists. It's deeply ingrained in physics, and scientists have yet to figure out how it could completely disappear. Science deals with the incomprehensible by breaking it down into manageable steps. The same applies to the end of time. Reflecting on time leads to a deeper understanding of our place in the universe as mortal beings. The qualities that time will gradually lose are essential for our existence. We rely on time's one-way direction for development and evolution, duration and scale for building complex structures, causal ordering for processes to unfold, and spatial separation for creating pockets of order in the world. As these qualities erode, so does our ability to thrive. While we can imagine the end of time, no one will directly experience it, much like how we cannot be conscious at the moment of our own death. As our distant descendants approach the end of time, they will face increasing challenges in a hostile universe, and their efforts will only speed up the inevitable. We are not passive victims of time's demise. We contribute to it through our existence. We convert energy into waste heat, contributing to the universe's degeneration. Time must cease for us to continue living. And that's it for this video. Thanks for watching, and be sure to subscribe for more videos.